Welcome. Today is Wednesday, June 28th, 2017, and this is the NERI Early Career Researcher Forum. This forum is intended to foster the exchange of ideas and be a platform of best practices for successful research. It is intended to highlight compelling research, build up the natural hazards engineering student community, and provide presentation opportunities. For more information, visit the NERI website at DesignSafe-CI.org, where you can find links to the SimCenter and the NERI Learning Center. Today's webinar is coordinated by the Natural Hazards Engineering Research Infrastructure's Simulation and Computational Modeling Center. This webinar is supported by the National Science Foundation under awards 1612843 and 150817. Any statements in this webinar are those of the presenter and do not necessarily represent the views of the National Science Foundation. Today's presentation is by Zach Camanyo-Withall, a first-year doctoral student at UC San Diego. Zach is working with Professor Joel Conte on reliability-based seismic design. His research focuses on probabilistic modeling and analysis in the context of performance-based earthquake engineering. The title of his presentation is Uncertainty Analysis of Structural Seismic Response Parameters Using High-Throughput Computing. And Zach, at this time, I'll hand the presentation over to you to begin.
All right. Thank you, Matt, and good afternoon, everyone. So the focus of my presentation today is on uncertainty quantification and propagation, specifically in the context of structural and earthquake engineering. So some of the things I'll be talking about today borrow concepts from those fields, not necessarily specific to structural engineering, namely probability theory, computational statistics, and computer programming. So I am in some ways still a novice on these other topics, but I want to demonstrate how someone with a working knowledge of the core principles can use tools from each to advance their research. So this is the outline of my presentation. I'll begin by briefly discussing different types of uncertainty and the scope of the presentation. I will then show how I have incorporated uncertainty quantification into my own research, going over the structural model that I use in the OpenSeas framework, ground motion record-to-record variability, and then I will follow this up with a comparison of results between a deterministic and a random structural model. I will conclude my presentation by discussing the tools that have made my research possible, specifically the implementation of parallel computing and a open source software called Dakota. And for Dakota, I will discuss in detail how I've interfaced it with OpenSeas. So before jumping immediately into my research process and the results, I'm going to briefly cover two classifications of uncertainty. So epistemic uncertainty, the first type, can be described as uncertainty in a model or modeling process that captures the key phenomenon or features or information that you're interested in. And this uncertainty can be that the model fits the data, which generally arises due to lack of data or data scarcity. It can also be uncertainty over which of two competing models is better or more accurate, or maybe even the uncertainty that the model itself is accurately capturing the key phenomenon. And these generally arise due to a lack of knowledge. So therefore, these uncertainties are often classified as reducible because further information reduces the level of uncertainty. An example could be something like the estimated worldwide average height of adult men, where you have to get a sample size of the population in order to estimate the true value, and that estimate has some error, the extent of which is uncertain. The other type of uncertainty, which is going to be more the core focus of this presentation, is aleatory uncertainty, often called natural variability. It describes inherent randomness in any process or experiment. Meaning that no previous knowledge of the process or experiment can definitively predict with 100% certainty future states or outcomes. So these types of uncertainties are therefore classified as irreducible, and perhaps an example of aleatory uncertainty is the number of earthquake occurrences in a given region over an exposure period of 100 years. If we If we expect the estimated rate to be about 1 every 100 years, we might see none, or we might see several, but we're most likely going to see one, but it can fluctuate is the main point. So this is Peer's performance-based earthquake engineering framework, which many of you are likely familiar with. The framework assesses the future expected performance of the design, more used for retrofit, but they're starting to build in a recursive, iterative, forward inverse design process. So the framework essentially works by one-step memory, where the seismic hazard depends, for example, the seismic hazard here depends on the location and the design. The structural response hazard depends solely on the intensity measure from the previous step, etc., through damage analysis and through loss analysis. So the focus of my presentation is going to be particularly on the seismic hazard analysis and the demand hazard analysis. So here is a simple three-dimensional structural model that I've used as a benchmark for the purpose of illustrating how uncertainty quantification can be applied to time history analyses. So it's a 2x1 bay steel frame, which was designed using the design code for Seattle. All members are wide flange shapes. The beams are made of A36 steel and the columns are made of A992 steel. The fundamental vibration period is 1.52 seconds, and we will be subjecting this model to bidirectional ground motion records. So all members in my structure are modeled using one element. It's a nonlinear fiber discretized force-based beam column element. It uses 7 Gauss-Lobato integration points, and they also employ the P-delta nonlinear geometric configuration and a linear elastic section aggregator for shear and torsional behavior. And you can also see the fiber discretization right here. So we have 24 fibers in the bottom and top flanges and 12 fibers within the web. The fibers employ the Meneghetto-Pinto uniaxial stress-strain relationship, which accounts for strain hardening once the steel is yielded. The material parameters illustrated here, for example, Young's modulus, the yield strength, and the hardening ratio are going to be modeled as random variables. We're going to do this both for A36 and for A992. And yeah, so let's look at how they can be modeled with uncertainty. Parameters subject to uncertainty are modeled as random variables. A random variable is a variable that can take any number of possible values. A realization of a random variable is a specific value that that random variable takes. So for example, if we're considering the elastic modulus of steel to be a random variable, then a realization might be 29,200 KSI. And since some realizations are more likely than others, a likelihood distribution must be identified. 2 of the most common ones are the uniform or equally probable distribution, or the normal bell-shaped distribution. These uniform and normal distributions are examples of probability density functions, or PDFs. PDFs are characterized by their distribution parameters, for example, the mean or the standard deviation. So here the mean or the standard deviation here. The area underneath the distribution within a set interval describes the probability of being within that interval. So for example, the probability of being within 1 standard deviation of the mean is about 68% for a normal distribution. And since the PDF must define all possible outcomes or realizations, the total area underneath it must be equal to 100%. And finally, a common way to convey the dispersion of these distributions is to normalize the standard deviation by the mean. This is known as the coefficient of variation, and it provides a more intuitive measure of the uncertainty or variability as a percentage of the expected or mean value. So for my structure, to reiterate, I model Young's modulus, the yield strength, and the strain hardening ratio separately for A992 and A36 as normal and log normal variables. You can see their means and the coefficients of variation. The yield strengths, I took the expected values, not the nominal values. And we also chose to model the equivalent viscous damping ratio of the structure as a random variable. We employ Rayleigh damping, so it uses the 2 fundamental translational modes, and we have a mean value of about 2%, coefficient of variation around 20%. I just want to key you guys in real quick, and some of these variables have higher coefficients of variation than others. Young's modulus is around 3%, it's pretty low. Yield strength between 5 and 10%. So really the variables with high variation are the strain hardening ratios and the damping ratio. And also we can define correlations if we have statistically dependent data. For steel, this is not a concern, but for concrete, you might have, for example, Young's modulus and compressive strength that are very positively correlated. So that has to be defined as well. And now, even though we have clearly defined all the random variables, this alone is not sufficient for an OpenSees analysis. As we know, OpenSees requires specific numerical values in order to run. It doesn't have any understanding of distributions or means or anything like this. So what we have to do is we have to give it actual numbers to work with. So to do this, we're going to employ Monte Carlo simulation and use a technique called sampling, where random number generators via the computer draw realizations from a target probability density function. These will be drawn such that OpenSees has actual numbers to work with, and if we were to plot a histogram of all of the input realizations, say we took 1,000 of them, the histogram would approximately look like the target PDF. So we're accounting for the variability, but we're also bringing in actual physical numbers that OpenSees can use. So the way the process works is you generate realizations of the random variable. This is just going to be a case where we have a single input and output random variable just to make it a little bit simpler for the time being. So we're going to generate realizations of the single input random variable, import it into the analysis software, run the analysis, and get some output realization. This output realization is going to be a derived random variable, and when we run many realizations through our analysis software, we're going to have variability on that output response, and that's what we're looking to measure here today. In the case of multiple input and output random variables, it's easiest to consider the multiple random variables as a single input random vector and multiple output random vectors as random variables as a single output vector. So this is an example of a random vector. Each index is simply the random variables themselves. And yeah, so you essentially put the random variables in the indices, and the ith realization of this input random variable completely defines the ith realization of my structural model, because these are the only parameters that change from one model to the next. So this is all that has to be defined for a new structure to be generated. And Monte Carlo simulation in general, it's completely numerical, and it has no real limitations. It could take any class of random variables, discrete or continuous, and there really doesn't seem to be any limit to how it can be applied. It's very robust as well, meaning that it asymptotically converges to whatever you're trying to estimate as you increase the number of samples. So the only real disadvantage with it is that it's highly computationally expensive and prohibitive, especially for a structure that has like many degrees of freedom or many fibers. But this high computational expense can be remedied either by employing a more refined sampling method, such that you can get the same degree of accuracy with fewer samples total, or by parallel computing, so you can run your samples simultaneously, or combinations of both. And I'll return to that at the end of the presentation. So now I'm going to discuss how the uncertainty in the seismic loading is accounted for. So the main goal when selecting design ground motion records is to consider an entire range of seismic hazard levels. Each hazard level is quantified by an intensity measure, the most common of which for our field is spectral acceleration. And the value of the spectral acceleration, it's either calibrated by design codes, by ASCE, or some sort of supplementary seismic hazard analysis. I will focus more on the latter, specifically probabilistic seismic hazard analysis, or PSHA, and we're going to construct what's called the uniform hazard spectrum from that. So PSHA quantifies the annual rate of exceedance of the spectral acceleration by accounting for all possible sources of seismic activity and their associated rates of occurrence. For each source, all magnitude and site to source distances, those scenarios are accounted for, as well as the aleatory uncertainty of the spectral acceleration given these sources and scenarios. And the annual rate of exceedance is found by scaling and summing the contributions of all of them, essentially. So here, plotted here are several spectral acceleration hazard curves, which correspond to different natural periods. Seismic hazard curve is simply the annual rate of exceedance on the y-axis versus the actual ground motion measure on the x-axis. So intuitively, as the ground motion acceleration increases, we expect them to be less likely annually, which is why these are dropping down. And if we want to construct a uniform hazard spectrum, as pictured here, we have to specify a particular hazard level that we want to fix. So I choose a 475-year return period, and I'm only going to be considering one hazard level for my analysis. So I pick the 475-year return period, and I essentially am going to be finding where all these hazard curves intersect this line. And so at 0 seconds, which is the peak ground acceleration, we intersect here, which corresponds to this point. And we can do it again for the 0.2 second spectral acceleration, the 1 second, and the 2 second. And this is the UHS for a 475-year return period. So then we can just enter with our structure's natural period of 1.52 seconds, and we got to target a spectral acceleration of around 0.28 g. So the UHS on its own isn't really that helpful when you're trying to select specific ground motion records. This is because the UHS is an envelope spectrum. It's equally hazardous at all periods, and as we know, earthquakes are generally peaked at a few locations, but not everywhere. So what we're going to use is something called a conditional mean spectrum to have a more physically representative spectrum that we can then least squares fit ground motion records to, such that we can adequately get the natural variability, but also the expected average response for our structure. So to construct the CMS, we first have to do a deaggregation of the seismic hazard. This essentially just finds how much of what percentage of this total was contributed by each magnitude and distance pair, and we bin them such that we can find controlling pairs or average pairs that impact our structure. So this scenario is then used to create a preliminary spectrum that we will subsequently scale to create the CMS. This preliminary spectrum is this black line right here. It's the unconditional mean spectrum corresponding to my mean M and R, which is 7.5 magnitude and about 68 kilometers. And again, here, this red curve is the UHS. And these black curves, all these are the probability density functions of the spectral acceleration at a given period. So if the period is around 1 second or 1.2 seconds or whatever this is, then the spectral acceleration has this distribution. You can see it's peaked somewhere around here, and it could be a little higher or a little bit lower. This is that aleatory uncertainty that we're talking about here, conditional on M and R. And so then what we do is we choose to condition the ground motion records such that they have to go through my target period. This way I'm ensuring that I'm getting the target spectral acceleration at the period that I care about, and I'm going to relax my hazard constraints elsewhere. I'm going to let this dip off a little bit such that ground motion records that are more peaked in this region will be selected, and they're allowed to taper off just a little bit away from that period. And we also noticed that the conditional PDFs of the spectral acceleration become more peaked near this conditioning period. They're more narrow band, but away from the conditioning period, we still see that they're fairly broad as they were before, between this figure and this figure. So the inputs required to perform a PSHA and construct the resulting CMS curve are given here. You have to define your location, your VS30 site class, return period, and these are just the minimum requirements. The more you know, the better. If you know exactly some causative faults and exactly their distances away, that's more information. That's even better. But these are, at a minimum, you need to have these values in order to do a CMS. So you need the mean representative M, the conditioning period, the mean R. You have to pick a ground motion prediction equation or several ground motion prediction equations. And for my analysis, I use the USGS hazard tool, both for the hazard analysis and for the deaggregation. So I chose 50 ground motion records for my analysis, and here I've pictured the spectral acceleration of each record. These are selected using MATLAB software developed by Professor Jack Baker at Stanford. And you can observe that the response spectra, they have both the desired mean response, the center of all of these different ground motions kind of aligns well with the CMS, which is what we want, but we're also allowing them to have that record-to-record variability within the range that we want that record-to-record variability. So all we're doing is being consistent between our goals and our actual analysis sub-steps. So for a deterministic model parameter analysis, each ground motion is applied to the same deterministic structure, where the deterministic structure is created by using just the mean model parameters. So that's going to result in 50 time history analyses total, because there's 50 ground motion records. For a random model parameter analysis, we want to subject each ground motion to a variety of realizations of the random structural model. I selected 48 random structural models per ground motion, and that results in 2,400 different time history analyses with 2,400 different ground motion, 2,400 different realizations of the random structure. I'm not using the same 48 on all 50 ground motions. And I included this slide just to illustrate my workflow. So recall that a realization of the model is completely defined by the input random vector. So what I do is for ground motion 1, I generate 48 structures. The subscript denotes the ground motion number, the superscript denotes the structure number, and I do the same thing with ground motion 2 and all the way through ground motion 50. This results in the 2,400 time history analyses, and these will then result in 2,400 recorded EDP random vectors. EDP is engineering demand parameter. So now that we've covered model parameter uncertainty and record-to-record variability, we can compare the results from the deterministic and the random parameter analyses. So the EDPs that I will be focusing on are the peak absolute floor acceleration envelope over each floor, as well as the maximum peak floor acceleration over all floors. So for brevity, I will refer to this complete overall maximum as just the peak floor acceleration, or PFA, and I'll use the word envelope whenever we're looking at individual stories. Likewise, I'll also be looking at the interstory drift ratio envelope and the maximum interstory drift ratio over all stories, which I will call the peak interstory drift ratio, or PIDR. And all of these EDPs were measured in both the transverse and longitudinal directions. So for each time step, I took the magnitude of the vector that they formed in the XZ plane, and I took a maximum over the whole time history. So these are vector drifts and vector floor accelerations. So here I've plotted 6 representative ground motion specific PFA envelopes of the 50 total. So for example, ground motion 3 is subjected to 48 structures. So the 48 different envelopes that were a result of those 48 analyses are pictured here in blue. The mean of those 48 is this black line here, and the red one is the result from the deterministic model case where the mean model parameters were used. And we can see that they align well, which corresponds with the assumption of a first order approximation. And we also can note that for some of these ground motion records, the model parameter uncertainty seems to play a relatively small role, particularly for, say, ground motion 24 or ground motion 8. We're not seeing a whole lot of variability on the EDPs just from model parameter uncertainty. But for other ground motion records, say, for example, ground motion record 31, we see a lot of variability on the second floor's peak floor acceleration. So this could indicate that in some instances, model parameter uncertainty can have a tremendous effect, and other times it has a negligible effect. And the purpose of looking at the plots like this is that you are isolating the effects of model parameter uncertainty. So you're cutting out record-to-record variability for each of these plots. This is just the uncertainty due to the model parameter uncertainty. And we can also look at all 2,400 envelopes at once and compare them to the 50 deterministic envelopes. And what we can see from here is that the scatter is relatively similar between the two. There are many more blue curves than the red curves, but they still cover the same broad range of accelerations along every story. So since they span such a broad range, several of the statistics that I measured for these EDPs are relatively identical between the deterministic and the random structural model. For example, the mean over all 2,400 random cases and the mean over 50 deterministic cases gets roughly the same number on each floor. Likewise, the coefficient of variation does not change much between the deterministic and the random structural model. One thing I do want to note here, it is kind of interesting, it's a bit counterintuitive that the random structural model actually estimates a lower coefficient of variation than the deterministic case. This is counterintuitive because we're introducing more uncertainty, not less. So you'd expect more uncertainty on the output, but we believe that this might be due to small sample estimation uncertainty with respect to the number of ground motion records that were selected, particularly for the deterministic case. A greater number of ground motion records could very well push the results in the other direction. And also remember that even though these results are very identical to one another, any given ground motion record can still have a lot of sensitivity to the model parameter uncertainty on some floors or some stories. And I also show the maximum overall 2,400 and maximum overall 50 deterministic runs. And we see that the maximum is higher for all of the random cases as we expected, the absolute maximum, which corresponds out here. So these versus this red one right here. I did the same thing with the peak and story drift ratio. At each story, I selected 6 representative ground motion records, a few that have almost no sensitivity to model parameter uncertainty, others where on one floor you see a range from 4 to 6%, so that's not negligible by anyone's standards. And so now we can also look at all 2,400 realizations of the inner-story drift ratio envelopes compared to the 50 deterministic envelopes. And again, we see that they cover the same scatter. The maximum for the random cases, the absolute maximum is again going to be larger on each story as expected, but the means and the coefficients of variation are going to be very similar once again. So now, oh, sorry, I went too far. So going beyond acceleration and drift envelopes, we may be more concerned with the probability of exceeding a particular acceleration or drift, and by extension, the effect of model parameter uncertainty on these probabilities. So to illustrate these probabilities of exceedance, I need to add to some of the probabilistic theory I previously covered. Recall that the area under a PDF corresponds to a probability of being within that set range. So since we're generally more concerned with being above or below a threshold rather than within an interval, it's convenient to introduce something called a cumulative distribution function, or the CDF. The CDF is simply the integral of the PDF from the leftmost limit to some undisclosed upper limit. And the CDF value at the leftmost end is 0, and it's 1 at the uppermost end. So the best way to visualize it is to just see how the CDF transforms as the area is fleshed out underneath the PDF. And so the height on the CDF, this height of around 80% corresponds to the area underneath here. So this is about close to 80% of the area underneath the total curve. And since the question is more commonly formulated as the percent chance of exceedance, it is more intuitive to use what's called the complementary CDF. And this is simply 1 minus the CDF. So it went from 0 to 1 before. Now it's going from 1 to 0, and it's just the complementary information. It's the probability of being greater than a specific threshold. So we can see how the CCDF decreases as the right tail is what we're starting to focus on. So on this slide, I am only considering the probability of exceeding a certain peak floor acceleration threshold. I have the deterministic results on the left-hand side, both the top and bottom, and the random model results on the right-hand side. And we can see that there's many more realizations here than here as expected. And on the top, I have the PDFs, the empirical PDFs, which are normalized histograms. And on the bottom row, I have the complementary CDFs that correspond to these numerical PDFs. So now a normalized histogram can be fitted using kernel density estimation, and this is an approximate continuous PDF of those results. And then we can define our limit state, which for me, I chose to be 1G on any floor, and we're concerned with being greater than this value. So in the deterministic and in the random case, we can either choose to fill in this area up here under the curve, or we can read off the complementary CDF function values at the corresponding x coordinate, which is 1G. And we can do this for both the deterministic and the random model. And we see that the deterministic model actually estimates a higher % chance of exceedance than the random model, which again might be due to small estimation uncertainty. A good way to think of the small estimation uncertainty is to look at this value here of 80%, or 8%, my bad. 8% of 50 realizations is only 4 realizations. So if we happen to have a 5th one in here or one less in here, so 5 or 3, this result could have been 10% or 6%. It's very sensitive to just 1 or 2 data points. So it's not that good of an estimate. This one is a bit finer. As you can see, it has like a few more digits to it. And also the kernel and the histogram are more in agreement here because there's more data. Here there's a greater discrepancy between the two, and that's again due to the small sample estimation uncertainty. I did the same thing with the peak interstory drift ratios. I selected a limit state of 3% on any story, and again, we can flesh out that area on the upper tail, or we can read off the complementary CDF values. And here we see that the values are in much greater agreement. This is likely due to this not being as high of a fractile as on the previous plot. Now we're dealing in the 26% range. We have more data points that are above this 3% drift. We have actually 13 in the deterministic case. So 13 is a better number than 4 because it's less sensitive to a small increment up or down. And again, we have very good agreement on the random model results. Now we are also probably more interested in the joint probability of either exceedance, not necessarily one at a time. Looking at one at a time is kind of limiting because as designers, we want to ensure that all of our bases are covered. So in order to look at more than one EDP at once, I have to, again, add a little bit to the probabilistic theory that we have been talking about. In particular, I have to define a joint PDF, a joint CDF, and a complementary joint CDF. So the joint PDF is nothing more than a higher dimensional PDF, and it considers only 2 variables at a time in the bivariate case. And where earlier we were finding the area under a curve, now we're going to be finding the volume underneath a surface, and the total volume underneath the surface is equal to 1. And this little cap symbol that you see here, what this means is the probability of x1 being between a1 and b1, and at the same time x2 between a2 and b2. So it's an intersection of events. It's the 2 happening at the same time. Okay. And now, just like how in the univariate case, we had a PDF with a CDF, now we have a joint CDF for our joint PDF, and now it's the joint probability of either value x1 or x2 being less than some threshold. So it's the, again, the intersection between the 2. And finally, we can define the complementary joint CDF as 1 minus the joint CDF, which asks the probability of either variable exceeding its corresponding threshold. So now notice that the cap is a cup. This means and or. So asking the complement of the probability of neither EDP exceeding its threshold is asking the probability that either EDP, one or the other or both, exceeded their threshold. So it makes sense intuitively. You can graph it, or you can use something called De Morgan's rule to prove it. But either way, we're just looking at And now, though I won't consider more than 2 variables at once in this presentation, I just want to note that these multivariate statistics are not limited to 2 variables. There's no upper limit to however many random variables you can look at once. The only thing is that you can't visualize them, so we don't have surfaces anymore. We're going to have hypersurfaces, and it just gets very mathematically cumbersome. So we're only going to stick with 2 EDPs here. So now we can look again at our deterministic case versus our random case, and we can start to plot the estimated joint PDFs, which are the normalized 3-dimensional histograms. So here I have the random case, and here I have the deterministic case. And we can immediately see that the deterministic histogram is much coarser than the random histogram, and this is again due to significantly fewer sample points, only 50 here versus 2,400 here. So the densities are not only different in terms of the peak estimates in the same region, but yeah. So we can also look at the top view just to look at the density in a different way, where we're just looking at peak flow acceleration and peak inter-story drift ratio, where the color is telling us how dense of a region that is. So now we can define our limit state as either being greater than 1G or 3% inter-story drift, and essentially we're going to be finding the volume underneath the bivariate histograms in these 2 shaded regions. So in the bivariate histogram we have 26%, and in the random case we have 25.5%. And like we did for the univariate case, we can fit some joint PDFs by kernel density estimation to these histograms to get an idea of the dispersion. So what I want to quickly note on is that for the random case, the kernel density estimate is 26.6% chance of exceedance versus 25.5%. On the flip side, in the deterministic case, the kernel is estimating 30.2% versus 26% from the histogram. So again, we're seeing a greater discrepancy on the deterministic case, which is due to the small sample estimation uncertainty. Moving on from this joint PDF, again, integrating a region, especially one that is not just one region, but really like 2 or 3 here, it can be very cumbersome, especially if we want to evaluate the percent chance of exceedance at multiple design points. So it's, again, useful to use the complementary joint CDF, where we can simply measure the surface function value at a specified location. And these are integrated from the kernel density estimates of the joint PDF, so the results are identical. So I just want to conclude on my results by saying that a general computational framework has been assembled that combines uncertainties of the model parameters and the loading. And by general, I mean that the framework works for any OpenSeas model and any number and class of random variables. It also allows for EDPs to be quantified by statistical descriptors, and it's completely open source. So the model doesn't necessarily have to be from OpenSeas. For you wind engineering people, the loads don't have to be earthquake ground motion records either. And specifically for my research, overall, I found that the record-to-record variability dominates the aleatory uncertainty of the EDPs, and it kind of outweighs the contributions from the model parameter analysis when all the ground motion records are considered at once. But again, any individual ground motion record can still be sensitive to this model parameter uncertainty. Part of the reason why we also think that the model parameter uncertainty was outweighed by the record-to-record variability was because those input random variables had lower coefficients of variation, as I previously alluded to. So we're looking to next apply this framework to a reinforced concrete structural model. Concrete obviously has a lot more natural variability because it's not as controlled of a structural material. So there's going to be higher coefficients of variation, and we're also going to have positive correlations between some key parameters, which will most likely increase the failure probability. And now I'm just going to show how I acquired all these results. So first, I will talk about Dakota. So Dakota, it's a multi-purpose, multifaceted toolbox of algorithms for a variety of different applications. Obviously, uncertainty quantification, but you can do sensitivity analysis or design optimization, etc. There's also, for uncertainty quantification, it's not just sampling, sampling in the classical sense, like crude Monte Carlo or Latin hypercube. You can do adaptive sampling if you're building a surrogate model. You can do importance sampling if you're sampling a region of low probability. You can use both local or global reliability methods. And there's also options for epistemic uncertainty and mixed epistemic aleatory uncertainty. There's also additional resources for getting started in troubleshooting. In particular, there's a user's guide, which goes over essentially everything that the program has to offer. There's a theory manual to cover the theory behind any of these applications. And there's also a reference manual to cover any syntax type questions, so you know exactly how to code it. There's also an email list for questions and queries, and it's community driven mostly. So essentially it's fostering collaboration between different researchers from different institutions such that they can help one another answer each other's questions. So you can put yourself on this email list if you want to participate. So specifically, how do you implement Dakota and how do you interface it with OpenSeas? There's a variety of methods, but essentially what you have to do is you have to provide paths of communication between the two software. And there's multiple ways to interface it. For sampling, it's probably easiest to think of Dakota wrapping around OpenSeas. And by wrapping around it, I mean that it'll perform all of the pertinent pre and post processing. It's going to generate those input files, and then it's going to call OpenSeas as a subroutine. So it's wrapping around and it's just calling it in the background. And once it exits, then it's going to post-process and export those results back to Dakota. So it's essentially wrapped around OpenSeas, and that's probably the easiest way to implement it. The main Dakota input file, it's going to define what type of method we're doing. So for me, I'm doing sampling. I'm going to request 48 samples for any job submission. I'm going to give it a seed number so I can reproduce these results if I want to, and I'm going to use Latin hypercube sampling. You also have to define your random variables, in particular their names, which have to be, they're case sensitive, and these have to be the same as what they're written in OpenSeas in order for the two to communicate with one another. Variables is also where you define the names of the variables, or the distributions rather, the normal distribution or the log normal distribution, means, standard deviations, upper and lower bounds if you don't want to consider values outside of a certain range, etc. Now, you also have to define the interface section over here. And the interface section, essentially, this is where you're going to be setting up all the pathways of communication. You got your analysis driver, which calls OpenSeas. You're also going to be defining your work directory such that the results can be obtained automatically rather than you having to, flip through 2,400 different results files. So this is just essentially allowing the two programs to communicate with one another easier. And you finally have to define any responses that you want Dakota to do the post-processing on. So if I want the peak floor acceleration or the inner-story drift ratio to have some statistics measured on them, I'm going to put these here. You can also optionally use another software like MATLAB to do the same stuff if you prefer. And now the analysis driver, it pre-processes a template file such that it can be interpreted by OpenSeas. So real quick, the template file, you can see it's written in the Tickle language, set your variable, then whatever the number is going to be. These curly braces just tell Dakota to substitute in the realization here. And so the first line in the analysis driver just pre-processes it into the Tickle file, and then the second line calls OpenSeas via the command line and gives it the input file, the Tickle file that will source this parameter.tickle file within it. Then all you have to do is run your simulation. So you just call Dakota on the command line, you tell it the input file, dakota.in, and the output file to store the results. And then Dakota will pre-process for a few seconds, and then it'll run OpenSeas in the background. It'll wait for the exit flag from OpenSeas, and when all the simulations are done, it'll search the current work directory for the EDPs themselves. It can then perform any statistics that you want on it, empirical PDFs or CDFs, moments, confidence intervals. There will also be an output file which essentially summarizes the entire analysis. So how much wall clock was used, how many CPU hours, the assignment of jobs to cores in the case of parallel computing, what were all the realizations of the random vectors, etc. And it'll also provide a restart file in the likely case that some of your OpenSeas analyses crash. And so to conclude, I will now end on parallel computing. So as previously stated, the problem with Monte Carlo simulation is that it is computationally inefficient, particularly when you have to have a high number of sample evaluations and where each one is time intensive and run sequentially. So for my simple structure, the average runtime was about 2.8 minutes, but if you multiply that by 2,400 analyses, then that equates to almost 5 days where you're waiting on your results. And obviously, in the grand scheme of things, 5 days for people in our field, that's not a whole lot of time to wait. But if your structure is, you know, like a large structure and the runtime is maybe a day, then that would take years to conclude such an analysis, and that's completely unacceptable. So since each analysis is independent from one another, you can minimize your total runtime by maximizing the number of cores that you have access to. So optimally, I would have one core for each analysis, and in such a situation, the total runtime would be the duration of the longest analysis, which for me was around 10 minutes. And the gains from parallel computing can be very, like, you know, they're very obvious just from that. So you can wait 1 day for your 2,400 analyses of your really large scale structure by running them all in parallel, essentially. And the only way to access these resources is by cloud computing, supercomputing, or cluster computing. You have to abandon doing everything on your own computer or on your own network. You most likely do not have access to enough cores to really see the full benefits of parallelization. The differences between cloud-based computing, supercomputing, and cluster computing are not really that important. They're not really the focus here. Essentially, they're just different flavors of getting you the resources such that you can run your jobs simultaneously. And as a researcher, gaining access to these resources is fairly easy. Since these resources are government or national laboratory or university financed and managed, they're intended to be for researchers. So if you are a researcher, it's pretty easy to get access. Examples of these resources include Stampede by TAC. We also have a supercomputer on my campus at UCSD, the San Diego Supercomputer Center. And you can also use computer clusters like the Open Science Grid. So essentially what you have to do is shop around for a supercomputer or a cluster you're interested in using and just apply for an allocation online. An allocation just dictates how many annual resources that you can use. And they're generally free or inexpensive for small to medium-sized workloads. So for my allocation, I'm on Stampede through TAC. It was granted to me through DesignSafe under the NARI umbrella. And I have a maximum of 50,000 annual CPU hours at no annual cost to myself. I highly recommend using Stampede since Dakota is already set up on their system for parallel applications, and they also have OpenSeas and MATLAB. MATLAB, it's pretty hard to find supercomputers that actually have MATLAB. It's one of the few, if I'm not mistaken, that actually has it. So you can do all your post-processing on the supercomputer instead of having to transport gigabytes or even terabytes of recorded data back to your computer. So it's just expedited. And remember, these are shared resources. There's hundreds of researchers logged in at once. And so it's best to practice good citizenship. Don't overload the system and don't run anything on the login nodes because those are shared resources. So these systems, they generally run Linux. I've only seen Scientific Linux or Red Hat, but I'm sure there are many other distros that are used. And so you're going to need to remote login via what's called an SSH client into a login node. These login nodes facilitate the user interaction with your job submissions to the main supercomputer. And this generally will require a Linux emulator if you're running Windows or Apple iOS, since Linux commands cannot be understood by Windows and iOS. The architectures are different between the systems. The job submissions are relatively straightforward. You can just use the secure copy command in Linux to transfer all your files over to the login node, and then you're going to run them on the execute nodes. You're going to submit the jobs via a job scheduler. Stampede uses Slurm. Other supercomputers use HT Condor, if that's one that you're familiar with. They both do pretty much the same thing. They add jobs to a shared queue, and they assign your jobs to inactive execute nodes as these resources become available and once it's your turn. And it's all automated such that it's essentially optimized. I think they have around, it's in the upper 90s, the percentage of CPUs that are being used at once, like of the total system. It's in the upper 90s. So they're pretty good at maximizing how many people can use the resources at any given moment. And obviously, the more resources that you request, the longer your queue time. This is going to discourage overuse and inefficiency. So an example Slurm file, this is one of the ones that I use to get my research done. These S-batch things that look like comments are actually not comments. These tell the system what my allocation is, or how much total wall clock time I'm allowing, how many total parallel processes I want, how many nodes that I want, in this case 3, etc. And there's also this command that I have to execute just before calling Dakota. It's called IB run. Some of you might have seen MPI run on other systems. They both do the same thing. It's just executing the following command in parallel, essentially. So just to illustrate now, finally, my workflow with the implementation of parallel computing, we take our 50 ground motion records. They're going to have 50 separate job submission files assigned again to 48 structures. These 48 structures with the associated ground motion record are going to be assigned to all of these different CPUs. This is assuming one CPU for all of them simultaneously, but it doesn't necessarily have to be simultaneously. Some jobs might run sooner than others. And all of these CPUs will be running until they get the EDPs that we want. And then at the very end, step 3, all these EDPs come back to Dakota, and this is where the results file is. And that's pretty much it for me on this presentation. I'd like to acknowledge a few people, Matt Schottler for facilitating this webinar, Tim Cockerell, and the system administrators at TAC for getting Dakota on there for me, DesignSafe for the free allocation, as well as my advisor, Professor Joel Conte, Rodrigo Estrosa, Frank McKenna, and also my fellow graduate student colleagues. So thank you for your time, and I'm glad to take any questions that you guys might have.
Great. Thank you, Zach, for the presentation and for all the information you provided. At this time, we'll open up the question and answer session. Attendees are reminded that questions should be submitted through the chat panel and sent to the moderator, since you'll remain in listen-only mode. So Zach, the first question is, comes from the uncertainty parameters and how these were determined, what ranges were used, and just where did you obtain those parameters? Do you have a reference for them, or are they just, yeah, where did you come up with those?
Right before I answer your question, I just want to make sure that I'm still sharing the PowerPoint presentation. So you can still see it, right? Now it's not full screen?
Correct.
Okay. So these material parameters were selected from literature. So I used the expected yield strength, for example. So for A992, this is 55 KSI. The expected yield strength of A36 is really 54 KSI, not 36 KSI, which is the nominal value. So some of them were selected more for intuitive reasons. Others were selected from actual literature. This is where, that's specifically where we actually got the coefficients of variation. You can find good estimates of the means without having to look at that much statistical data. These are pretty easy to find, but the coefficients of variation, those came from literature because it's hard to estimate exactly how much variation or how much dispersion that we have. It's not something that's commonly used in these analyses. So this took a bit more digging to find, but the mean values are fairly straightforward. And the distributions are more so chosen based off of test data fitting and also a bit of common sense. So We use the normal distribution for example, for the Young's modulus because it's so far positive and it's fairly symmetric that this is a good approximation, but we don't use it for the yield strength because a normal distribution can technically go negative. Log normal keeps everything positive, and it also has a higher upper tail. So the choice of the distribution is also due to data fitting and a bit of good engineering judgment.
Okay. So another question is going to be, does Dakota create and distribute all of the 2,400 jobs, or do you use a separate script for that purpose?
Yeah, so the way I did that was I have one file that generates 50 Slurm submission job files, and each of those job files is requesting 48 samples of the random structure, and each job file is ground motion record specific. So I do have it automated so that even though I have 50 job submission files, I'm not writing them by scratch. The only thing that's changing is the ground motion record number and some things about the ground motion record, like the scaling of it in both directions or the name of it, so that there's no error in terms of I can't find the text file to submit, or to apply my ground motion record. So everything was automated as much as I could, but I still do have 50 submission files for 50 ground motion records. And each submission file is 48 jobs that it wants to run. So.
Okay. How are the mathematical models like Monte Carlo integrated into the simulation? Were they built into Dakota, or are they coded separately?
Well, Monte Carlo simulation, it's not really like something that has to be necessarily implemented. All you really need is a random number generator that can follow your target distribution. It can draw realizations from your target distribution. And then those numbers just have to be able to be put into your analysis. So Dakota, it implements sampling to get this done, but Monte Carlo simulation shouldn't be looked at as some grand thing that has to be set up and orchestrated in such a way for it to run. It's actually, there's as little like user interaction as possible. It's the most general case, which is kind of what I talked about here. It's general in the sense that we don't have to define that many things in order for it to run. So Dakota just generates the samples, calls OpenSeas, puts a sample into OpenSeas, waits for OpenSeas to finish, and then just reads the results. So that's pretty much it.
Okay. Have you considered high intensity or near fault ground motions which produce interstory drift ratios more than 3 or 4%? And comment along that question is that the running time for a single nonlinear analysis of 2.8 minutes seems relatively fast for a 4-story 3D building. So if you have any comments on that?
Yeah, so since each element is, or since each member is only modeled with one element because they're force-based, there's actually not that many total fibers in any given like iteration of the structural state at a certain time step. There aren't that many fibers. There are only around 150 degrees of freedom, if I remember correctly. I think a total of around 350 sections where there's Gauss-Lobato integration points. So the actual like level of complexity, even though it's a 3-dimensional structure with several bays and several stories, it has very, very few nodes and degrees of freedom and whatnot, such that my analyses can be run quick. Because again, it's just a benchmark structure. It's not really like a very advanced model. It's more just to demonstrate the capabilities of uncertainty quantification. It's not really a structure where we're looking to focus on or give specific importance to this structure necessarily. So it runs fast because it was designed to run fast, essentially.
Okay. How many of your CPU hours, you said you had 50,000, how many of those did you consume to complete this work?
So for this work, let me think. So if the average is, well, you can actually calculate, it's 4 days and 16 hours, right? Because the average times 2,400. So 4 days and 16 hours. So that's going to be 96 plus 16, so 112 CPU hours of the 50,000 were used for this. So I could reproduce this 8 more times to get to 1,000 times 50. I can do it 400 more times this year if I wanted to for free. And I'm not even sure that the 50% is like the highest that you can go without having to pay for something. I just know that that's the standard thing that they give out, where you can essentially get it with almost no effort on your part. It's not something where you have to apply and wait and stuff. It's like, oh, 50,000, no sweat. So, yeah.
What do you do in the case of non-converging time history analyses?
Well, that is something that I did not have to encounter specifically because I chose a steel structure. So that was another reason why we chose a steel structure first, because the Meneghetto-Pinto model has infinite strain hardening. So the convergence is almost never an issue. And on the few occurrences where it did happen, I reran the exact same Slurm job submission file, and I did not get an error back on the second run. So sometimes a few of your simulations are just going to crash, but I didn't change anything. I resubmitted it, and they came back fine. But for a concrete model, that's obviously going to be a much higher concern. It's a very brittle material, especially when it goes into tension and then back into compression. We're going to have some issues there. So we have not fully decided how we're going to tackle those issues yet. I'm going to try to find a way to automate it such that maybe I'll be measuring the recorded data of, say, a plastic hinge forming at the bottom, and we could see that if this convergence, this lack of convergence was due to a true structural failure, or if it was just a spurious calculation that got stuck somewhere on the time step. And then we can maybe, if it's the latter, then we can maybe change the time step a little bit and retry the analysis. But if it was due to a failure, then that's also good information to get as well. But trying to find a way to automate it, that's still something that we are in the process of thinking about.
Okay. Do you think it's possible to use Dakota to perform Bayesian updating to optimize a model using data recorded from sensors?
Yeah, it can do that. It has both, like I said, it has the epistemic uncertainty options, and that's really what Bayesian updating is about. It's about updating models such that we have lower epistemic uncertainty. And they have a few options for that. I know I've read Bayesian inference. I've seen they have something called Dempster-Schaefer theory of evidence, which I'm not familiar with. But you can also do interval analysis to bound your results. They definitely do have Bayesian capabilities, though. I haven't explored it for that. Like I said, I've been focusing more on aleatory uncertainty, but I've definitely seen the word Bayesian all over the user manual. So I'm fairly confident that you can use it for that.
Okay. How did you conclude that the engineering demand parameter is more affected by aleatory uncertainties than epistemic ones?
It's not necessarily that we included that it's more sensitive to that. It's that we were more interested in modeling how uncontrollable the inherent variability of the structural parameters. They're not I'm not trying to say that they're so uncontrollable, like we have no clue how strong this building is. I'm just saying that we were more interested in seeing how much of an effect the true inherent randomness that we usually model as deterministic features or values in our models. We were curious to see if we were to actually treat it the way it more physically should be treated, if that would have an effect. The epistemic uncertainty would come more in the form of, was this a good distribution to pick for this random variable? Or is this an adequate mean? Or is this an adequate coefficient of variation or a correlation between two variables? But I don't want to consider aleatory and epistemic on the same level because they're really answering different questions. And our question was more geared towards trying to make our model a little bit more physically realistic, just to see the effects. So. Okay.
Maybe just time for two more questions. One is, how did you produce the ground motion time histories from the spectra that you showed?
Oh, yeah, that's a great question. So like I said, I used Jack Baker's from Stanford. I used his MATLAB code to generate this. And so essentially what it does is, if I go to this slide real quick, you can see how at each of these different periods, we have a conditional distribution of the spectral acceleration. And so what we do is we actually even employ Monte Carlo simulation on this level. What we do is we generate a random point within this range. It's going to be most likely near the mean, but it could be a little bit higher or a little bit lower. We're going to also generate a point within here, within here, within here. We're going to fix this point, and we're going to also generate a point within here. And like I said, the points are going to be most likely near the medians, but they could also be a little bit higher or a little bit lower. And then what we do is we literally connect these points with just straight lines. Then we go to our database of ground motion records. We look at their response spectra. We do least squares fitting, and we find ground motion records that are closest to that randomly generated spectra that we created over these different periods. And yeah, you do that over and over and over, and you end up getting ground motion records that actually scale well at the target period, but they're also getting that variability elsewhere. So it's actually Monte Carlo simulation built into it. And I didn't discuss that because I didn't take up too much time.
Okay, one more question is, have you thought to do an inverse analysis to obtain these results? I'm not quite sure what the inverse analysis would be.
If they're referring to the performance-based earthquake engineering methodology, if they're talking about the inverse idea where the structure has yet to be designed and we are trying to gauge its future demands or future damage or future loss, then the modeling of the aleatory uncertainty is definitely geared towards that, because we're modeling, the Young's modulus or the yield strength as random variables. Once your structure has been built, you can put in sensors to better measure those values, and that's where we get into the Bayesian updating. So by looking at it more from an aleatoric perspective than an epistemic perspective, we really are doing that inverse problem already, where we're looking at how uncontrollable randomness can impact our answer, and then we're trying to adjust for that. So I might have misinterpreted the question, but if that was the question, then I hope that was an adequate response.
Okay, and then there's some interest in your reinforced concrete study that you mentioned. Mm-hmm. Is that something that is in the works, or is there an opportunity to share that in the future?
We can maybe do another webinar on the concrete model. I'm imagining there's going to be a little bit of work in terms of automating exactly like which simulations that we expect to crash, which ones were legitimate failures versus just spurious calculations. Also, the structure, it uses displacement-based elements. So a lot of the code that I've automated to expedite my my force-based steel model, I'm going to have to adapt it. But I imagine that since I've gotten a lot of the grunt work done for the steel model, redoing it for the concrete model is going to take a fraction of the time it did to get these results in the first place. So hopefully in the next 6 months is probably what we're looking at. Obviously time variant, but that is something that we're going to be doing soon, definitely within the next year.
Okay. Well, we're now at the conclusion of today's Early Career Researcher Forum. On behalf of the attendees, thank you, Zach, for taking the time to share your research. To the attendees, thank you for your participation and your questions. Please check the NERI website and check your inbox for emails from announce@DesignSafe-CI.org that will have registration links for additional upcoming webinars in the Early Career Researcher Forum and the Natural Hazards Engineering 101 webinar series. Thank you for attending today's forum.